we good?
Yeah.
All right. Hello, everyone. Welcome back for session 3 of the ACT preparation course that you guys are taking. We're on section 3 for mathematics. So here we go. Just so you guys remember, my name is Tim. And you can reach me at inspiredclassroomtim@gmail.com. If you guys have any questions or concerns and you want to get a hold of me and talk about it, you can reach me there. So please feel free to do that. We have a lot to talk about today. We've moved on to intermediate algebra. Hopefully the last 2 sections of pre-algebra and elementary algebra were useful, and hopefully it was mostly a review. Everything on this ACT exam should be a review, hopefully, for you. Not to say these questions can't get super hard, but they're at least some sort of mathematical concept that you've seen or heard of in the past. So we're going to move on to intermediate algebra. These are the things we're going to try and get through for section 2. We got understanding the quadratic formula, rational and radical expressions. What does that mean? Absolute value equations and inequalities. So what does that mean and how do we solve those? We're going to talk about sequences and patterns a little bit, systems of equations, functions, roots of polynomials, and complex numbers. So this content is going to get trickier. It's going to get a little harder, and hopefully I can show you some useful tricks that when it comes time to take the test, you'll find some use for those. So without further ado, we'll get started. The first thing we're going to talk about today is understanding the quadratic formula. We talked last time in elementary algebra about factoring quadratic equations of the form ax squared plus bx plus c, as you can see right here. Y equals ax squared plus bx plus c. We factored equations like that in the form last time, so and I'm going to show you again how we did that and how that relates to this formula that you see down here. X equals the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a. So first we're gonna do a problem concerning that, showing you how they relate, solving it. So I'll show you the order of operations, or PEMDAS, using that formula, and then what it is that it's exactly getting for you. So the first problem we're going to talk about it's going to be a problem that I have here, but we're going to need to move to camera 2, so if you bear with me for a second. Camera 2, and there it is, hopefully. Perfect. Ooh, is there any way we can brighten this?
Let's see.
Sorry.
No worries.
This is pretty dark.
Oh yeah, we were messing around with it the other day. Let's see. The magic of technology.
That'll be better, for sure.
How's that?
That'll work. Perfect. So last time we were together, I showed you how to factor equations of the form a x squared plus bx plus c and we worked on a problem, I believe it looks similar to this. X squared plus 8x plus 15. And I showed you to factor this. I showed you that we needed to take the last term, 15, and find its factors. 1 and 15, 3 and 5. And of course, we needed to look through our factors and find the one that added to our middle term. So if you'll see, notice there that 3 and 5 equals 8. So we have x plus 3 and x plus 8 in our factored form. And if we FOIL that back together, FOIL, we get x times x, which is x squared, x times 8, which is 8x, x times 3, which is 3x. I'm sorry, this should be a 5. Which is 5x. Those were what my factors were. I messed that up. Sorry about that. And 3 times 5 is equal to 15. We combine our like terms, and we end up with x squared plus 8x plus 15. So we know that this is equal to that because we FOILed it and we factored it. And they're the same thing. Now how does that contribute to the quadratic formula? Well, I will show you. So the quadratic formula is used to solve equations of the form ax squared plus bx plus c equaling to 0. So it's more like an if-then statement. So if ax squared plus bx plus c is equal to 0, then x will equal the opposite of b plus or minus square root of b squared minus 4ac divided by 2a. So if ax squared plus bx plus c is equal to 0, then x is equal to the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a. So with our last problem, I had x squared plus 8x plus 15. And if I let that equal 0, then I'm in the form. If ax squared plus bx plus c equals 0, then I can use this formula, and then you can see here I have that case. I have 1x squared, which is a, plus 8x, which is b, plus 15 is equal to 0. So here we have a, here we have b, and this guy right here is c. Just keep in mind when you're doing this, we hold on to the sign. So if this is a negative 8, then you have to use negative 8 for b. If this is a negative 15, you have to use negative 15 for c. Similarly up here, if we have a negative x squared, then the coefficient for a is negative 1. So how do I use this in the formula? Well, I pick out my a, b, and c, and then I literally just drop them into the formula. So x then is equal to the opposite of b, so negative 8, plus or minus the square root of b squared, so 8 squared. Notice I separated my variable with parentheses. 8 squared minus 4 times a, which is 1, times c, which is 15. All of this is divided by 2 times a. So 2 over 1. So once we've got it put into the formula, now we have to use our PEMDAS, or our please excuse my dear Aunt Sally's, or my order of operations, better yet, to solve this problem. So the first thing we're going to do is we're going to do the exponents. As you can see, we have an exponent right here. So this tells us that x is equal to negative 8 plus or minus the square root of 64, which is 8 squared, minus we can actually do this part now because it's multiplication and we've already done the exponent. So 4 times 1 is 4 times 15 is 15, 30, 45, 60. And it's still being divided by whatever is on the bottom here, which is 2 times 1, so that's just going to be 2. So we've solved it a little bit. We're getting a little bit closer, but we haven't quite figured it out yet. So we'll move to the next spot. This is x is equal to 64 minus 60 under the square root tells us that we need the square root of 4 divided by 2. We'll figure out this square root. This implies that we have negative 8 plus or minus 2 divided by 2. And notice we have a plus or minus here. And it's important because when we factored the last time, and I'll show you that right now, we factored the last time, we ended up with 2 factors, x plus 3 and x plus 5. So this plus or minus is representing the fact that we have 2 answers to this equation. So negative 8 plus 2 is a negative 6 divided by 2 tells us that x is equal to negative 3, or negative 8 minus 2 is negative 10 divided by 2 is negative 5. So we get x equals negative 3 or negative 5. So there we've solved the quadratic formula for this problem. It was in the form of ax squared plus bx plus c. I set it equal to 0. I pulled my a, b, and c, plugged them into the formula, as you can see here, and then I carefully, step by step by step, solved for what x could be. So I end up with x is equal to negative 3, or x is equal to negative 5. Now if we look back at our factored form, this guy right here, x plus 3, x plus 5, I want you to notice that if I set it equal to 0, which is the rule for quadratic functions, if ax squared plus bx plus c equals 0, and I know that this is the factored form, x plus 3, x plus 5, well, in order for this to be 0, this term has to either be 0, and 0 times whatever this is will equal 0, or this term has to be 0. So 0 times this term is also 0. Hence we have 2 answers. So if I set this, if that's the case, then x plus 3 has to equal 0, which implies x is equal to negative 3. Or x plus 5 has to equal 0, which implies that x is equal to negative 5. Which is what I have here. That's where I have it right here. So the point of this is to show you that the quadratic formula is more useful than factoring because we don't necessarily have to have nice numbers in order to factor, or in order to use the quadratic formula. We can do it with fractions, we can do it with decimal points. The formula will always give us the solution to the quadratic equation. Now you're probably wondering what I mean by solutions to quadratic equations. So I'm going to swoop back to my PowerPoint here, camera 1, and then Whoops. What did I do here? This is what I
One
wanted.
moment, please. I don't know what did you do.
I hit directory accidentally. There we go.
Okay. One moment, please.
I was supposed to hit that one.
This guy.
Yeah.
Yeah. There you go.
All right.
There you go.
So the solutions, where am I at here? The solutions to, I'm sorry. How do I get this off of here? Oh, perfect.
Yeah, just click away. No worries.
So the solutions then are actually where x, the line x, where is it? Right there. Right there. That, my friends, would be one solution to this quadratic equation. Now keep in mind this graph that you see right here is not mapping the same equation that I just worked on, but if it was, my answers of -3 and -5 would be where this graph flies through the x-axis. I'll show you on my calculator here in just one second, but what I calculated, x equaling -3 and x equaling -5, are where we actually touch the x-axis here on this graph. So those are what we'll call solutions, or roots to the polynomial of the quadratic equation. So you might hear them said in both words, roots or solutions. I'll show you on my calculator. You can kind of see that. We had the equation y equals x squared plus 8x plus 15. If I hit graph, my window's a little, been using my calculator, but we'll zoom standard so you can see it. I'm going to turn my plots off so you don't have to look at those other things. And there it is. So notice, I calculated x equals -3 or x equals -5. If you count 1, 2, 3, there's the spot we go through the x-axis, -3, and 1, 2, 3, 4, 5. So what we're calculating here is the exact spot that this function, when graphed, hits the x-axis. You can use your calculator to, well, no, hold that thought, never mind. So, x equals -3 or x equals -5. We have a problem from the test that I sent, the pre-test. If any of you have had an opportunity to take a look at it, problem number 24 on the test looks like this. Zoom in a little bit, maybe. There it is, number 24. It says here, an artist makes a profit of 500p minus p squared dollars from selling p paintings. What is the fewest number of paintings the artist can sell to make a profit of at least $60,000? So the way I went about this problem was to set up the equation. And since P stood for profit, we had 500P minus P squared. And we wanted it to be at least $60,000. So as soon as I saw this, I noticed that I had a P squared, a P term, and a constant term. So for my purposes, I was thinking quadratic formula in order to solve this guy. But first, I have to get it in the right form. It says, if ax squared plus bx plus c is equal to 0. Well, this is not quite that form, but I can use some algebra and minus the 60,000 from this side. What I do to one side, I got to do to the other. So I'll minus 60,000 to this way, and I'll have exactly that. I'll have, with a little bit of reordering, which I'm allowed to do, I can have negative p squared plus 500p minus 60,000 now, and that is equal to 0. So now I'm in the form. If ax squared plus bx plus c equals 0, then I can use the formula of, in this case it's p, so p is equal to the opposite of b plus or minus square root b squared minus 4ac divided by 2a. It might be to you guys' benefit to try and memorize this formula, because quadratic equations will definitely be on the ACT. It's not fun memorizing it, but think of it like a song or something, and you might be able to come up with some creative ways to stick this to memory. It's certainly nice to have when solving quadratic formulas, especially if you're not a big fan of factoring, because the quadratic formula will get you the answer. Sometimes it takes a little longer, but it will definitely get you the right answer if you work through the steps correctly. So now that I have this, I'm going to plug them in. I have 500, so I have negative 500 plus or minus the square root of 500 squared minus 4 times negative 1. That's the coefficient. If there's no number there, it's 1 of this first term times negative 60,000, all divided by 2 times negative 1. Well, it turns out I did some math. So now we'll definitely need a calculator for this, but 500 squared is 250,000. So this next step should be negative 500 plus or minus the square root of 250,000 minus 4 times negative 1 times negative 60,000 equals 240,000. All divided by negative 2. Simplifying this a bit further, tells us that we're going to be taking the square root of 10,000 and still dividing by negative 2. Square root of 10,000 happens to be 100, I think, but we'll do this in the calculator to be sure. It's 100. And this gives negative 500 plus 100 is negative 4, divided by negative 2 is a positive 200. Or the other one, negative 5 minus 100 is negative 6. Divided by negative 2 is positive 300. So our profit is going to be either 200 or 300. Now back to the question. An artist making a profit, dollars from selling P paintings. What is the fewest number of paintings the artist can sell to make a profit of at least $60,000? So we want the fewest number, which happens to be 200. So 200 paintings to make $60,000. So that was number 24 on the ACT practice exam that I gave you. I used the quadratic formula to solve it. I had to manipulate a little bit. It wasn't in the form to start, obviously, from up here, but with a little bit of algebra, you can get it in the form, set it equal to 0, and now your formula works to solve for the problem. So back to camera 1 here. So you'll notice here I've got line of symmetry and vertex. So the vertex then is going to be this bottommost point. Or when you graph things of the form y equals negative x squared plus bx plus c, it's going to be the highest point. This thing will flip over if that a is negative. So the line of symmetry is going to be the line that goes right through the middle of this. And in order to find it, could very well be a question on the ACT, they might ask you for the vertex of something, which the vertex is this point right down here. If you're looking for that, all you need is the opposite of b, and then you divide that by 2a. That's where the x coordinate is going to lie. You take that x, plug it into your other formula, and out will pop your y coordinate. So the line of symmetry is always going to be the opposite of b over the 2a. That part is the line of symmetry, right through the middle. The discriminant is this part right here that you see, the square root. It's the b squared minus 4ac. You see the plus and minus right here. Well, the plus and minus is telling you how far from the very center we have to go in order to find our roots. So here's one root there from a plus, and there'll be another root there from the minus of the opposite of b over 2a. So the discriminant is telling us how far we are from the middle, from the line of symmetry, or the vertex, and it tells you exactly where they both hit the x-axis. If you do the whole formula, it tells you where it hits the x-axis. So this is a little bit on the quadratic formula. It takes some practice to get used to solving the quadratic formula. I'm sure that you have access to some books with quadratic equations in them. There's plenty of sources on the internet. Just type in quadratic formula, quadratic equations, and you'll have lots and lots of opportunities to practice solving these and getting the right answer and finding out exactly what it is that you are calculating. So that's a little bit on the quadratic formula. It will definitely be on the ACT. If any of this didn't make sense, or you want another run through with it, please email me. I will happily send you solutions, scan you solutions of problems that I've worked, and hopefully we can clear out any misconceptions that we may have. So that is the quadratic formula. The next thing we have to talk about is rational and radical expressions. So those are some fancy words. Rational expressions, I've broken this down into two spots really. First we have rational expressions on this side. A rational expression is where you are dividing, some sort of fractional expression. So here you've noticed we have x squared minus 6 divided by 7x. The important thing to remember when you have these is that there are domain restrictions. It's important to recognize that you cannot divide by 0. What does domain mean? Domain means where you live. In this case, in mathematically speaking, what we're talking about is what x's can we actually plug into this function or this equation that give us answers, right? So if you just look at the one that I have there, if I put in, that you see right here, if I put in 1 squared is 1, minus 6 is negative 5. Divide that by 7 times 1, it's a number. It pops out. We can do that. Unfortunately, though, we can't divide by every number. There is one number that we cannot divide by, and that happens to be the number 0. If we think about a pizza, right, and you want to cut what it is to have 1/8 of or a slice of pizza, you've cut a pizza into 8 equal sections, and you eat one of them. That's what a fraction is representing. In this case, we have a fraction bar, but if x is 0, we have a whole thing, and we've cut it into 0 equal pieces. That's not possible. That doesn't make sense to do. You can't have something and make it into nothing. So when I talk about domain restrictions, I want to talk about what x's can I plug into here that will give me a number. If I have an equation like x plus 5, well, it doesn't matter what number I plug in for x. There's always a number that when I add 5 to it, it pops out, and there's a nice y number that's just 5 bigger than x. In this case, though, if y is equal to x squared minus 6 divided by 7x, all the numbers that I plug into there, I can solve, or will give me an answer, except for one, and that happens to be 0. So generally, when we're solving problems of rational or radical expressions, the idea is to grab the denominator, or whatever's on the bottom, set it equal to 0, find out what x makes that happen, and exclude that from our domain. So we could have a function I will show you here from camera 2. We could have a function, say, y is equal to 3x plus 2 divided by 2x plus 7. And you might be asked to find the domain of this function. Well, what we would be mostly concerned about is if this part right here went to 0. So we would set it equal to 0. 2x plus 7 is equal to 0. Minus 7 from both sides. We get 2x is equal to negative 7. Divide by 2. Divide by 2. X is equal to negative 7 halves, or negative 3.5. And so our domain is all real numbers x except negative 3.5. Because negative 3.5 makes this equation it so this equation is being divided by 0. We cannot divide by 0. A little bit more proof that that's the case is on our calculators. If I divide by 0, I'll take my favorite number 11. I'll divide it by 0, and my calculator gives me an error. Divide by 0. You cannot do that. So this is how we find out what numbers we can actually plug in to our function, and will give us reasonable answers. So that's a little bit on domain. The idea is to set the denominator equal to 0, and you'll be able to find where this function will not work. So domain means what can we plug into this function that actually gives us, will spit out another number. And the big key here is remembering that we cannot divide by 0. It doesn't matter what the numerator is, 0 divided by something is still 0. But it's not the case the other way around. Moving on to radical expressions. Radical expressions are the ones that have this funky symbol in them that you see. Anytime you see this root symbol, we're talking about radical expressions. We can treat radical expressions, there's a little bit of tricks to them. We've talked last time about how we cannot break up the radical symbol over addition or subtraction, but we can break it up over multiplication and division. So let's work on a square root problem. We actually have one from our exam, our practice exam. So if you guys want to look at problem number 48, we'll take a look at that. Number 2, we'll look at problem number 48 here. Let's save some paper. There's number 48. It's got all sorts of radicals in it. That could be scary. This is actually kind of a pre-algebra problem. It's adding fractions. That's all we're really doing. So I hope you guys remember from last time, but adding fractions requires that we find a common denominator. Obviously, this question is towards the end of the test. It's a little bit tricky. But it tests your knowledge on roots and how you manipulate them. So I will rewrite the problem to start here. We had 4 over root 2 plus 2 over root 3. There it is. There it is, right there. The first thing I need to do in order to find a common denominator is I need to take the denominator from this side, multiply it top and bottom, and take the denominator from this side and multiply it top and bottom. So I'm going to, in a different color here, we'll use red. We'll multiply root 3 and root 3. And on this side we'll multiply root 2 and root 2. Now, when I said earlier that you cannot break up the radical sign over addition or subtraction, but you could break it up over multiplication, that tells me that this bottom part, it's already broken up. So this top part is going to be 4 root 3's, so 4 times root 3. And this bottom part is going to be now 1 root and 3 times 2 of 3 times 2. Plus, here we have 2 root 2. We treat our our roots of numbers like variables. It's just a number, but square root of 2 is such an ugly number that you wouldn't want to actually multiply it. And I will show you. 2, second square root of 2 is this horrible number, 1.414213562, and it continues on. It's an irrational number with no repeating decimal. But this number is not very friendly to work with when you're trying to multiply it because it's really big and long and you'd have to double everything and it's not very friendly. So what they do is they just hold root 2 in this form and say we're multiplying that by 2. So we're treating it as a variable, really, in a sense. And that's going to be over, well, once again, root 3 times 2. Well, 3 times 2 is 6. So I have 4 root 3 plus 2 root 2 all over root 6. Now that I have a common denominator, I'm allowed to shift everything up top, and everything is just over that one common denominator. I do believe this is a choice on our answer section. You could be asked to rationalize the denominator, which would mean you'd have to multiply top and bottom by a root 6 to clear this root symbol. But if you notice here, back to our answer sheet, my answer, 4 root 3 plus 2 root 2 divided by root 6. And you'll see right there, 4 root 3 plus 2 root 2 divided by root 6. So G. G is our final answer. So that's a little bit on... That is a little bit on radicals. Another thing that you might encounter is, say, oh, I don't know, times you might have to be asked to solve, or simplify the square root of, say, a number like 45. Okay? So this is a separate problem from the one we did last time, but solve or simplify the square root of 45. Square root of 45 is not a nice number, so I will show you. We can solve it in our calculators. Plug it in, square root of 45, hit the number, and we get 6.708203932. Of course, if they ask you to do this and all your answers are in decimal points, then plug it into your calculator and find the answer. But if not, they may show you that 45, they may have the answers looking like this. 45 is equal to 9 times 5. So this is the square root still of 9 times 5. And I've told you you can break up the square root symbol over multiplication, and we're having to multiply, so this is equal to the square root of 9 times the square root of 5. And the square root of 9 actually happens to be a nice number. So the point here is we're trying to find squares that when we take the square root of them, we still get a nice number. So if I take the square root of 9, I get 3. So here, this is equal to 3 root 5. So notice that this number, when I put it in my calculator, was 6.70820 ... Keeps going. And if I type 3 second square root 5 into my calculator here, like you see, if I did this correctly, it should be the same number. Look, 6. So this guy right here is also 6.70820 ... going on forever. So this is the simplified form of root 45. 3 root 5 is equal to the root of 45. Keep in mind you can do this over division. So if I had the square root of 16/25, well, that's the same as the square root of 16 over the square root of 25, which is 4 over 5. So the idea is we're looking for perfect squares. Perfect squares 1, 4, 9, 16, 25, 36, 49. This is 1 times 1. This is 2 times 2. This is 3 times 3. This is 4 times 4. This is 5 times 5. 6 times 6. That's what the definition of squared means, right? It's a number times itself. This will also pop up when we talk about sequences or series. This is a nice sequence. This is a nice sequence of squares. So it's good to know at least 1 through 12 what all the squares of those numbers are. Let's see, what else about radical expressions would be important? Go back to camera 1 real fast. People on content, perfect, okay. Alright, so square roots. And we'll talk about this little part right up here coming up in a little while when we talk about complex numbers. At the end of this lecture, square roots of negatives are imaginary numbers. So the definition of I is the square root of -1. So you may see problems where you have to, where you may have the square root of -4. Well, because we're allowed to break up this over multiplication, we have the square root of -1 times 4. That equals -4. So that implies that we have the square root of -1 times the square root of 4. So this number is actually the imaginary number of square root of 4 is 2, and I, this guy, is equal to I. So 2I is equal to the square root of -4. So we'll work on some complex number stuff in a little bit, but by definition, the square root of -1 is equal to I, which implies that I squared is equal to -1. We'll see that in a little while, but try and get comfortable breaking up your radical expressions over multiplication or division. You cannot over addition or subtraction. Notice when I did the quadratic formula a little while ago, I did not break anything up because we had a minus symbol in there. So I had to figure out what all that stuff was before I could take the square root of it. I wanted to talk briefly, I forgot one thing about rational expressions that I would like to show you. So going back to camera 1, people and content. So going back to this guy over here, these rational expressions where you divide by something, I'm going to run by a problem that I found that you may encounter on the ACT. So go to that. Color. Rational expressions. Cannot divide by 0. Sometimes can simplify. And I want to talk to you real quick about simplifying sometimes. Sometimes you may encounter an equation where y is equal to, say, x squared plus 25. I'm sorry, that should be minus 25. With the minus sign. Divided by, say, x squared plus 4x minus 45. I made this problem up myself. Hopefully, maybe you guys can recognize that this is a perfect square up top. So it actually factors nicely to x plus 5, x minus 5. So here we are factoring again. So it's a good skill to get used to. I'm trying to simplify this rational expression. So the first part up here factors to this. This bottom part, well, we're going to need our factors, negative 45. So we have 1 and 45, 3 and 15, 5 and 9. And if you look at those ones, 5, negative 5 and positive 9 equal negative 45. And negative 5 plus 9 is positive 4. So this is going to factor into x minus 5, x plus 5. And notice we have two terms here that are similar. So I can get rid of this. And this thing simplifies to x plus 5. Oops, sorry, gosh, I'm messing up a lot today. This is a 9 over x plus 9. Once again, if we want to find out the domain restriction, we take this part and set it equal to 0. Minus 9 from both sides, we get x equals negative 9 is out of domain. So there we have rational and radical expressions. It was a quick run through. There's a lot going on here. Obviously, you can imagine that things can be tricky. But with a little bit of practice, you will get more and more comfortable with working with these rational and radical expressions. So we'll move back to camera 1. Option, perfect. If you guys have any questions about rational or radical expressions, or you find you have any problems that you've been working on, shoot them to me. I will do my best to come up with decent solutions and send them your way. Again, my email, inspiredclassroomtim@gmail.com. I've sent you guys some stuff. Hopefully you've gotten it. And hopefully this is useful. We'll move on to the next thing that I have, absolute value equations and inequalities. So what is absolute value? Absolute value is let's go to this side. Ooh, this is kind of weird. Absolute value is the distance from the point to 0. So notice here that the absolute value, these symbols, these little bracket symbols that you see, they're not parentheses, they're just lines saying the absolute value of this thing. So the absolute value of 5, well, is 5. It's 5 units from 0. Similarly, the absolute value of negative 4, or for any negative number for that matter, is also it's positive. We're talking about the distance from 0. We're not talking about the sign of the number. Whether it's positive or negative, we simply want the distance from 0. So absolute values are always positive. The distance from the point to 0. Distance is always positive or 0. Now that's a pretty simple concept, but when it comes to solving these problems, it can be a little tricky. So I have picked a couple of absolute value problems, equations, and inequalities. The inequality is talking about this symbol right here, those less than or greater than symbols that you see. Those guys right there, those are inequalities. And there's a trick here to breaking up these absolute values with inequalities that will allow you to solve them. So I have a problem here. I want you to notice if multiplying or dividing by a negative while you're doing the algebra of simplifying x or solving for x in any way, if you notice that you are multiplying or dividing by a negative number, then that's when your inequalities have to go from one side to the other. Okay? Other than that, solving these is the exact same as we would solve them algebraically had they been equalities with an equal sign. So I have a couple of problems here that I'd like to show you. So we'll move to a different camera. Camera 2, we'll move that way, and we will do these problems in green, light green. So I'm trying to solve the equation, solve for x. And I have the equation, absolute value of negative 6x plus 5 is equal to 10. So the way that we get rid of these absolute value symbols is by breaking this up with a positive and a negative value. So this is going to tell us that we have negative 10 is less than or equal to negative 6x plus 5, which is less than or equal to positive 10. So now I'm solving this equation in two directions, but the idea is the same. I got to get x isolated all by itself. So I'm going to minus 5 from this side, minus 5 from that side. What I do to one side, I got to do the other. So this goes away. So my next line is going to say negative 15 is less than or equal to negative 6x, which is less than or equal to 5. And here, I'm dividing by a negative. Like I said before, we got to be careful when that happens. We divide by a negative because it's going to flip our inequalities. So what's going to happen is negative 15 divided by negative 6 is 2.5. And this guy gets flipped now. This is canceled. X is this way, and this it gets flipped. And we're dividing by negative 6. 5 divided by negative 6 is negative 0.8333. So this says to us that x is greater than negative 0.8333, but it is less than 2.5. Since these were straight up equal signs, you can change these back now to equal signs. So we get x is equal to 2.5 or negative 0.8333 repeating. So that's the way we deal with absolute value. Is you have to break it up over an inequality. You have to compare it to both the positive and the negative of whatever it's being compared to. So that's how we'd solve that one. Let's do one more. I have one here where it says solve for x. And we have the absolute value of 2x minus 14 is equal to 10. So notice here our absolute value signs they don't look the same as our last problem here. We had all of this stuff in the absolute values. Over here now we just have this stuff in the absolute value. So it's important to recognize where that is. I can't break it up yet because it has to be just absolute values on one hand side. So in order to do that, I'll add 14. Add 14. So now I have the absolute value of 2x is equal to 24. Yes? Now I can do my trick of breaking it up on both sides. So I have negative 24 is less than or equal to 2x, which is less than or equal to positive 24. So now the only difference is I don't have my absolute value symbols in here, and I'm comparing both the negative and the positive. Divide by 2, divide by 2, and divide by 2. Notice I'm dividing by a positive number here, so I'm not going to flip my inequalities because the only time I do that is when I divide or multiply by a negative while solving. I'm solving for this, and I'm not dividing by a negative, so my inequalities are going to stay the same. Negative 24 divided by 2 is a negative 12. and 24 divided by 2 is a positive 12. So x is going to be between negative 12 and positive 12. And since we were looking at an equal sign from the very beginning up here, an equal sign, we can say x equals negative 12 or positive 12. So that's how we solve absolute value problems. We have to break them up and solve them both for their positive and for their negative. I hope that's useful. Let's see what else we have to talk about. Camera 1. Alright. Hello, welcome back. Here I am. So, as you can see, they did it a little differently than I did. But the idea is the same. They're breaking it up. Notice that negative 2x minus 3 is less than 5. It's also greater than negative 5. So they're doing it in a little different order than I am, but it's still the exact same. So if you have questions, please shoot me an email. If any of this seems a little confusing, we can try and clear it up with a little bit of practice and a little bit of communication. The next thing we have to talk about are sequences and patterns. We definitely have seen at least one sequence on all the ACT practice exams that I've looked over. I haven't seen any that are different than this. So you can expect to see at least one arithmetic sequence, which is of the form y equals mx plus b, which hopefully you guys know is the form of a line, right? So it's just linear, it's just shooting up, it's always constant. So you might have a series like 3, it starts at 3, and then it goes to 6, and then it goes to 9, and then it goes to 12. Well, what's happening is it's adding 3 every time, right? We're adding 3 every time. Notice I have the squares sequence up here, 1, 4, 9, 16, 25, 36, 49, 64, it goes on and on and on. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. The geometric sequence is probably the one that might throw you most for a loop. It's of the form a equals b to the x. That one we're going to talk about right here in a minute. It's one of ours on the practice test that I gave you. So yeah, we're going to take a look at that. The last thing is the Fibonacci sequence. So the Fibonacci sequence is the sum of the last 2 terms. So 1 and 1 is 2. Let's see if I can find it here. 1 and 1 is 2. 2 and 1 is 3. 3 and 2 is 5. 5 and 3 is 8. 8 and 5 is 13. 13 and 8 is 21. And on and on and on and on it goes. Sequences don't ever end. What does sequence mean? Sequence is one number after another, after another, after another. So if you guys would like to look at number is it? Oh, sequences and patterns was number 7. Number 7 on our practice test. We'll take a look at that real quick. It's a tricky one, I thought. Some of you may have noticed it right off the bat. Here we are in number 7. There it is. The first term is 1 in the geometric sequence. 1, negative 3, 9, negative 27. What is the 7th term of the geometric sequence? So they give you 4 terms, and it is our job to figure out what is the 7th term. Now right off the bat, they told you geometric sequence. Geometric. So that means we have y equals, you can't see it, but it's some number a, b to the x. Okay? That's the definition of a geometric sequence. So what's happening here? We have 1, -3, 9, -27. So what is the pattern? So if x is 0, and it always starts at 0, okay? Sequences always start at 0. So if we say this is 0, then b to the 0 is going to be 1, because anything to the 0 power is 1. So we're starting at x equals 0, so we have y equals a b to the 0. And we know that we know that 1 is equal to a b to the 0, and -3 is equal to a b to the 1, and -9 is equal to a b squared, and -27 is equal to a b cubed. So this is our sequence. We have 1, -3, 9, -27. We must know, and we have to put this to memory, but anything to the 0 power is 1. So I know that b to the 0 is 1, and so I have 1 is equal to a times 1. So a must then be 1, because 1 times 1 is what's 1. So I know that a is equal to 1. A is equal to 1. Now looking at the second term, if a is equal to 1 and b is equal to -3, well, -3 to the first power is -3. So 1 times -3 squared. So I feel like I'm getting this. I have a as 1, I have b as -3, and I know what my x's are. So let's see if this is going to work out. Well, -3 squared. Well, -3 times -3 is a positive 9, because a negative times a negative is positive. And -3 times -3 times -3 is equal to positive 9 times -3, which is equal to -27. So this sequence now is turning out just how the pattern said it was going to. -3 cubed is -27. So here I have 0, 1, 2, 3, 4, 5, 6, 7. I want my 7th term. This was cubed, 4, 5, 6. So my 7th term must be -3 times 1 to the 7th. Get my calculator out. Type in -3 to the, there's our to the button right here. Right, there's the to the button. 7th power. And I went too far. I'm sorry. We want the 7th term. So 1, 2, 3, 4, 6, 7. Look at that. We have to count 0. So I want this to be to the 6th. I'm sorry about that, guys, but this is to the 6th. -3 to the 6th power is 729. Equals 729. And of course it helps when looking at the answers if 729 is a choice. So E, this is how we solve these. A geometric series or a geometric sequence, if it doesn't say geometric, it's going to grow and get a lot bigger than an arithmetic sequence because of the power. The power is telling you to multiply things again and again and again and again, and it's going to shoot up, and it's going to be a really high number really fast. So if you're looking at your pattern and you notice that this thing is growing, and this thing is growing quite rapidly actually, that's going to tell you that you're probably looking at a geometric sequence. If it's growing at a steady rate, that's going to tell you that you're growing at an arithmetic sequence. Blech. That's a horrible word. So that's how we deal with sequences. I haven't seen anything but geometric and arithmetic sequences in the ACTs that I have looked at. 729. Markers had it. Go back to PowerPoint. Here we are. So welcome back. So that was sequences and patterns. Let me know if you guys have any questions about that. Notice in my print here there's the to the button. You'll see that. That's on a keyboard. This guy right here, this caret, means to the power of. So you may see that. It's also on your calculator for what that's used for, to the power of. Let me know if you guys have questions about sequences and patterns. Once again, it's something that you can get used to. Some people are really good at seeing patterns right off the bat. Some people are not. It takes practice. For all of this stuff, it takes a little bit of practice. It can be a little overwhelming at first, but once you see it, it's not going to change. So let me know if you guys have questions. That's inspiredclassroomtim@gmail.com. The next thing we're going to talk about is systems of equations, everybody's favorite. Problems that involve multiple equations and multiple unknowns. There's one on your practice exam that I have right here. Number 15. So we're going to talk about, there's three methods for solving these. You can graph them over here. Both equations must be written as y equals mx plus b. You put them in your calculator, and sure enough, they will meet somewhere, and wherever they meet is where your answers are. You can single out substitution. This is how I will probably solve this one. Single out x or y and create a blob is what that says, but really you solve for x in one equation and then you sub it in for the x in the other equation, or vice versa. Solve for y and then sub the y in for the other equation. The final thing you can do is elimination. You can line them up, look for matching coefficients, and add or subtract to eliminate. So we're going to go to systems of equations problem right now, and I'm going to show you how to solve it by substitution, because that is probably the most straightforward method. Camera 2. So if you take a look at our problem here, number 15, zoom in, here it is, really big. This month, Cami sold 70 figurines in two sizes. The large figurines sold for $12 each, and the small figurines sold for $8 each. The amount of money he received from the sales of the large figurines was equal to the amount of money he received from the sales of the small figurines. How many large figurines did Cami sell this month? So I'm going to solve this problem. And I'm going to solve it in blue. And I'm going to say, okay, let x equal the large figurines. And let y equal the small figurines. And we know from the problem that she sold 70 figurines. So the amount of large figurines plus the amount of small figurines has to equal 70. Cami sold 70 figurines in 2 sizes. The large figurines sold for $12 each. So 12x has to, and the small figurines sold for $8 each. The amount of money received from the sales of the large figurines was equal to the amount of money that she got from the small figurines. So here's our system of equations. We have the amount of large figurines plus the amount of small figurines, and it equals 70. And then we have the price paid for the large figurines, and it's got to equal the price paid for the small figurines. So here I have 2 equations and two unknowns. Both equations revolve around x and y, and both equations have an x and both equations have a y. So, and the x and the y's represent the same thing in both equations. Furthermore, so here I'm going to solve by substitution. So I'm going to pick an equation. I'm going to pick this one. And I'm going to say this implies, that's what that symbol means there, this implies that x is equal to 70 minus y. Right? 70 minus y. So now I can substitute x in other equation, in the other equation. Now, notice this problem started as a story problem, and generally system of equation problems are story problems. And setting them up most of the time is a huge portion of the battle. So once again, that comes from reading skills, being able to understand what it is that you're reading. But setting up the problem is going to be, for a lot of people, the more difficult part than actually solving it. Once again, it takes practice. I would find systems of equations story problems either online or in a book that you guys have at your school. There'll be a whole section on it, so you can find plenty of practice for reading story problems and being able to figure out how to set these problems up. So now that I have solved for x in one equation, I can substitute x in for the other equation. So really, down here I have 12. Instead of x now, I have 70 minus y is what x is. So I can sub that in, 70 minus y, and that is equal to 8y. So now I've changed my problem from having x's and y's to a problem with just y's, and I can actually solve that problem. Now we can solve it. So I'm not the greatest at arithmetic, so I'll do 12 times 70 to distribute this. I get 840. So 840 minus 12y is equal to 8y. I can add 12y's to both sides to combine like terms. So this tells me that I now have 840 on the left-hand side and 20y on the right-hand side. Divide out by 20. Divide out by 20. 840 divided by 20 is 42. So y equals 42. Unfortunately, we solved for y, which is okay. We'll use that. But the question was, how many large figurines did Cami sell? And y represents the small figurines. So we know she sold 42 small figurines. All we have to do now is plug this y back into our equation for x. So x is equal to 70 minus 42, which is what y is. And 70 minus 42 is 28. So x equals 28, and Cami sold 28 large figurines. So that's how we solve that problem by substitution. And this was by substitution. $28 figurines. Another way to solve this is by graphing. Notice your graphing calculators. If you hit the y equals button, it's got a bunch of y equals stuff in it. So in order for us to solve this problem by graphing, we actually have to have all of our equations in y equals form. So I can show you how to do that real quick. We had x plus 7, or I'm sorry, cross that out. We had x plus y equals 70, and we had 12x is equal to 8y. So we'll get these in y equals forms. I'll minus the x. This is y equals negative x plus 70. And if I get this one, I get y is equal to 12 over 8x. Now that they're both in y equals forms, I can graph them. So I will graph them. I have y equals negative x plus 70. And I have y equals 12 eighths x. I hit graph. And of course, nothing happens. The reason nothing happened, well, I got a line, so that was all right. But the reason nothing happened is because my window is too small. So I have to zoom out. And we'll make my window bigger. And then you can see up there in that corner something happened, and then in that corner something happened. So maybe we can zoom out a little bit more. I'm just hitting the zoom feature on my calculator here, guys. Zoom out. I hit it again, and there we're getting something that might actually happen. So now that I've got two lines that are intersecting each other, I can find out where that intersection is. I can actually hit second calculate. If you scroll down to number 5 here, you'll see an intersect, and it'll ask you first curve, and you can see my little arrow moving around. You see him coming down right there. I'm going to tell it the first curve is right here. The second curve is right here, and then it asks you where to guess. Guess where your spot is, and I hit right there, and it says no, your intersection is x equals 28 and y equals 42, and that's what we solve for. We solve for x equals 28 and y equals 42. So you may need to replay this video to see what buttons I hit to be able to do this on your calculator, but your calculator will, if you can graph your system of equations under y equals, you'll get two functions, as they're called, two picture lines or whatever, and where they meet, where they intersect, that's the solution that you're looking for. So there I've shown you two ways to solve systems of equations. There are other ways. If you're interested, shoot me an email. These I find to be the most effective ways of solving. If you have the technology and a calculator, substituting is just a wonderful algebraic trick that is useful. So systems of equations, number 15 on the practice test. How we doing? We got a few more things to talk about. Oops, let's see. Camera 1. And then people on content. Alright, systems of equations, guys. If you guys have questions about those, please email me. I will happily answer all questions that I can. Functions. So I keep using this word function. Every time I graph something, it's a function. Every time it's y equals something, it's a function. And so you're probably wondering what the heck is a function. In functions, in math, the way I like to think about them is vending machines, right? If we hit A1, out pops our Doritos. And if we hit A2, out pops our Ruffles. And if we hit A3, out pops some Sun Chips. And if we hit D12, we might get some gum. If we hit C4, we might get a Hershey's bar, right? So this is how a vending machine works. If you tell it what you want, it outputs something accordingly to what you put in. mathematical functions work the same way. All these graphs that I've shown you, all these equations where y is equal to something with x's in it, these are all functions. You can imagine how frustrating it would be if you put your money in and you had a salty tooth and you really wanted those ruffles that are lined up in A2 slot, and you hit A2 and out popped the candy bar in D12. You'd be like, well, wait a minute, that's not how that was supposed to work. So then you hit A12, you put more money in the machine to get those ruffles because you still have that salty treat, and you hit A2 again and out pops whatever gum is in C4. You're like, well, this machine is clearly broken, right? So that's the way functions are as well. If you decide, okay, y equals some mx plus b, and you decide x is 2, well, then some y pops out according to that x being 2. Now, if you decide that x is 4 and out pops the same y, well then, if you decide x is 2 and out pops some y of, say, 7, and then you plug in x is 2 again, and out pops a different y of, say, x is equal to 12, or y is equal to 12, then your function is not, it's doing what these vending machines are that are broken. It's not being consistent. So when we're talking about functions, you need to talk about one input corresponds to one output. Now the output can be the same. I can fill a vending machine with all Coca-Cola, and it doesn't matter if I hit C1 or A2 or B3, everything is spitting out Coca-Cola. Well, the problem would be is if it was the other way around. If there was a bunch of stuff in there, and no matter what button I hit, different things were popping out. So we'll look at our ACT tests for a minute. But the important thing is one input, one output. It can't be the same input and two different outputs. Okay? That's the important thing when you're talking about functions. And there's a couple of problems on our practice exam that I'll take a look at that represent functions. You may not be able to tell because they're not graphs of things. Problem number 11 has a table. If I can find problem number 11, here it is. Problem number 11. Problem number 11 is representing a function. So your input is t, your output is 14. Your input is, for t equals 0, is 14. For t equals 1, it's 20. For t equals 2, it's 26. Now it would be weird if this was a 2 and then this was a 32, because it would not be a function if we plugged in 2 and we could get multiple answers. One input, one specific output. Solving number 11 is not too solving number 11 is a slope problem, and we'll talk about slope in our next section. But I wanted you to look at this table because it's representing a function. It's got one input or one output for each input, one different output for each input that's given. Let's see, number 16. Number 16 is quite similar. If you look at this, a car accelerated from 88 feet per second to 220 feet per second in exactly 3 seconds. Assuming the acceleration was constant, what is the car's acceleration of feet per second from 88 feet per second to 220 feet per second? Once again, this is a function. I notice I notice that I have the point 088 and the point 220. In order to solve this problem, I can do slope, which is y2 minus y1 over x2 minus x1. Most of these functions can be solved, or function problems are lines and they have slopes of lines. But once again, this is the input, okay? Input, or in our case it's time, and this is the output, speed. So functions are input, output. We want to be careful of inputting something twice and getting two different answers. Sorry.
You're fine.
I think I'm getting there.
It's a lot of math.
It is a lot of math.
It's a lot of good math.
I mean, basically what's on the ACT is anything that you've learned from the first grade on is fair game. So it's not meant to be easy, but it's also not meant to be impossible. Here I am. A couple more things. Matrices. Matrices will definitely be on the ACT exam. We have one on our practice exam. The important things about matrices is you can only add or subtract matrices of the exact same size. So I always talk about them by row by column. Okay? So you have so many rows, divide it, and then you have so many columns. Your calculator can actually you can input matrices, you can input the size, you can input the numbers into them, and it can do matrix multiplication and all that good stuff. We have a problem on here that I'll show you how to solve. It's also important, I want you to notice this image that I have here. You can only multiply matrices if columns in first matrix match rows in second matrix. So R by C, so 4 by 4. So if you're trying to multiply a 1 by 4 matrix times a 4 by 4 matrix, you match these two inner terms that you see here, right here, 4 and 4. You match those, and the resulting matrix is going to be whatever's on the outside. So, and that's what happens when you multiply. It's important to recognize that fact. I saw an ACT question, not one that we've worked on yet, but it asked if it was possible to even multiply these matrices together. And the quick trick, right, is looking at the size of the matrices and determining, well, if this matches this, then this is going to be the resulting matrix. So let's take a look at our matrix problem that we had on our practice exam. It is problem number number 45. Problem number 45. So we'll zoom in. Maybe. There it is. I see it. There's those matrices. Whoa, whoa. Too much zoom. All right. Given that A, some number A times this matrix, this is a 2 by 2 matrix. It's got 2 rows and 2 columns. And it's equal to some X, Y, Z, 27 matrix. So what is X plus Z? For some real number A. So how did I solve this problem? Let's take a gander. This is called scalar multiplication. So you can multiply a matrix by some number like A. And it's really easy. All you do is multiply everything in the matrix by whatever A is. So, let's zoom out here. We have A in some matrix 2, 6, 1, 4, 2, 6, 1, 4, and it's equals 2x, 27, y, and z. So I said, okay, well I know that if I distribute this in, that this is 2a is equal to x, because that's going to be that term. 6a is going to equal 27. 1a is going to equal y. And 4a's is going to equal z. So here I can solve for a, actually on this one. So this guy tells me that a is equal to 27 divided by 6, which happens to be 4.5 maybe. Let's see if that's true. 27 divided by 6, 4.5. There it is. So a is equal to 4.5. And our goal was to find x plus z. X plus z. So I need z and I need x. So x is equal to 2 times 4.5. And z is equal to 4 times 4.5. 2 times 4.5 is 9. 4 times 4.5 is 18. 18 plus 9 is 27. So that's some matrix scalar multiplication. I'm allowed to distribute this guy in to each term, and my resulting matrix is going to be whatever this is. So x is equal to 2a, y equals 1a, 6a is 27, and 4a is z. Once I have solved for a, I can find y and z. Add those two numbers together and you get 27. So D here. D is 27. Just to explain a little bit more about what I was talking about matrices of the same size, or different sizes, rather. You could have a 2 by 3 and a 3 by 4. So a 2 by 3 would look 2 rows by column, so 2, so A, B, C, D, E, F, right? So 2 rows, 3 columns. And this would be 3 rows, so we'll do A, B, C, D, E, F. Three rows, 4 columns. So, but the point is, since these match, since those match, we both have 3's. When we multiply this thing, our resulting matrix is going to be some 2 by 4 matrix. Get the outsides is what we get. And to multiply them, it's row by column. So you have to do what's called the dot product. So we'll simplify this a little bit. 1 by 3 and a 3 by 2. How about or we'll just do 1, 2, and 3 in that one. And this is 3 rows by 2 columns, so 1, 2, 3, 4, 5, 6. 3 rows, 2 columns. So our resulting matrix, since these match, is going to be a 1 row by 2 column matrix. And the way we find out what that is we do row by column. So this is 1 times 1 plus 2 times 2 plus 3 times 3 for the first part of our matrix. And then it's 1 times 4 plus 2 times 5 plus 3 times 6. So we have 1 row, 2 columns. We solve what these are. Notice I did 1 times 1 plus 2 times 2 plus 3 times 3. And then I did 1 times 4 plus 2 times 5 plus 3 times 6. So this is 1, 8, 9, let's see, 9, 10, 14. 9, 10, and then 4 is 14. 6 times 3 is 18, plus 10 is 28. 18 plus 10 is 28, plus 4 is 32. So if I wanted to multiply these two matrices together, I end up with the matrix 1432. These two on the inside need to match, and the resulting matrix is going to be whatever's on the outside. And it's row by column. Multiply each row by each column. And sum. So that's a little tricky, but I'm going to show you real quick how to do that in your calculator. So let's see if I got it right. I made this up off the top of my head, so I could be wrong. We have so there's a matrix button right there. Let me see if I can get this to where you guys can see it. It's in blue. It's in blue. It's above that. So I actually have to hit the second button, matrix. And my matrices will pop up. You can see that I have a lot of matrices I already typed in here. Our first one's a 1 by 3, so I'll scroll over to edit, right? Edit my 1 by 3 matrix. There you see it pops up. There's 1 row, 3 columns, and I said these numbers were 1, 2, and 3. Oops, I put a parentheses in there that doesn't belong. So there it is. My matrix A has now got 1, 2, and 3 in it. I'll quit, go back to my regular screen. Hit second matrix again, pull up, and now I got to edit matrix B here. It's a 3 by 2, which is already happening for me, so that's good. And I said this was 1, that was 4, that was 2, that was 5, that's 3, and that's 6. So now I've inputted my matrices into my calculator. If I want to multiply them together, I just go ahead and grab them. So second matrix again, grab matrix A, there it is, times second matrix, grab B. So there it is, matrix A times matrix B. I hit enter, and sure enough, 1432 is our matrix that comes out of that. So your calculator will add, subtract, or multiply all matrices for you, as long as they have numbers that you can input. The first problem we did was a bunch of variables. This case, we can add and subtract, multiply. We can even multiply them by a scalar. Check it out. If I do 5, second matrix A, 5A, it multiplied everything in my columns by 5. 5, 10, 15. It was 1, 2, 3. Now it's 5, 10, 15. So that's a little bit on matrices. I'm sure you've seen them before. It may have been a while. They can be complicated or they can be easy. So let me know if you guys have questions. inspiredclassroomtim@gmail.com. I'm more than willing and ready to help with anything that I can, for sure. There's my bald head. Look at it. Nice and shiny. These lights. Nope. I'm almost. I got roots. I'm not going to do any problems with this. This is going back to our quadratic functions. I want you guys to know that solutions is roots, which is x-intercepts, which is zeros. So they can ask you to solve for these equations with any one of these words. They might ask you for solutions. They might ask you for roots. They might ask you for x-intercepts. They might ask you for zeros. Really, they want you to find the spot on these functions. Find the spot on these functions where these things go through zero. Right here. Oh, you can't see that. That's crazy. Where they go through zero. This is our sine function. They go through zero. Quadratic functions we worked earlier. Notice this one touches zero, stays there for a little while, and shoots back off. Linear functions shooting through. So I wanted you guys to know roots of polynomials. If you hear the word roots, they're looking for where it's touching the x-axis. I also put on here a family of functions. These are all these different functions you can graph in your calculator. This is this one over here is y equals x. This is y equals x squared. This is y equals x cubed. This is sine of x. This one down here is cosine of x. We have what your rational functions look like. So notice that they're shooting up in one area and shooting down in the other. This spot right in the middle, right here, this is where they're dividing by zero. So there's no solution, right? No solution when dividing by zero. That's why this function goes off in two different directions. Rational functions, meaning we're dividing something. We cannot divide by zero. We have exponential functions, so your geometric series. Now I told you during our geometric sequences that they would shoot off really fast. Well, that's what this graph is representing. It's getting bigger and bigger and bigger as x slowly gets bigger. Okay? And the last one here is a logarithmic function. I don't think you'll have to be too worried about those, quite possibly, but notice it's our slowest moving function. It creeps to infinity quite slowly. One reason I wanted to show you this is because I want to show you some calculator stuff, and we're going to focus on y equals x and y equals x squared just for a second, but I want to talk to you guys about shifts in your graphs and how they happen. So we're going to do, well, first off, I'm going to do y equals, I'm going to set my window to standard, zoom standard. So that's my normal 10 by 10 window. I'm going to graph y equals x, and we're going to see that line shoot right through there, just like you guys, so it looks just like we just saw. Now, let's do some observation here. If I add x, say, plus 5, what's happened, my line is the same, but it's shifted up 5. So x plus 5 on the outside there has shifted my line up. Let's see if that theory holds true for, say, maybe x squared. I graph it. There it is. It's a parabola shooting upwards, like I said it would be. Now let's see what happens if I do x squared plus 5. Notice it's a shift. It's the exact same graph. It's just a shift upwards. So instead of hitting down here at 0, I hit down here at 5, or up here at 5. That being said, the number on the outside is graphing the plus 5. Let's say I decide to do something like x plus 2 squared. Let's see what that does. Put it in some parentheses. Well, that was a shift to the left. It was a plus 2, but notice it shifted it to the negative side of the Cartesian plane here. If I decide to do x minus 2, squared, it'll be a shift to the right. So notice the exact same graph, but I'm shifting it depending on what I'm putting in here. So in the parentheses here, it's a shift left or right. Outside the parentheses, it's a shift up and down. Let's see what happens if I make negative x squared. Oops, squared. Oh. Y equals negative x squared. Graph it. Well, that's going to take my original x squared function. It's going to flip it. So now it's shooting down on the shooting towards negative infinity as opposed to positive infinity. I think it's important to get comfortable with these families of functions, not because I want you to memorize the functions, but to get comfortable with how they move up and down depending on how you type them into your calculator. What's giving these things the right to move left or right or up or down. Another one is I can take 0.5. Let's clear some of these out so that it's not quite so convoluted. We'll have our base function, x squared, and we'll do 0.5x squared. So that's half of x squared. And here's our first function. That's our normal one. And check out what the second one is. It's widened it. It's stretched it out by a factor of 1/2. So let's see what happens if I make it 3x squared. Notice here, it's shortened it. It's shrunk it down, and it's shooting off to infinity much faster because now we're multiplying it by 3. So notice, I would get comfortable playing with your calculator and seeing what different shifts are created by adding or subtracting in different spots. And use your parentheses, use scalars, that's what this 3 and this 1/2 is, and stretch and shrink your functions and get comfortable with what's happening there. We're almost done. It's a lot of stuff. We're getting into the nitty-gritty of algebra, and you guys have been learning for 12 years now, and I'm trying to give you a quick review in a little less than 2 hours. So if you guys want this to be the most useful, definitely continue practicing. Unfortunately, the best way of getting good at math is by doing math, but that's the case generally for most of our endeavors. One last thing to talk about today, and of course that's the complex numbers. I told you that the square root of -1 is equal to I, so you can see that right here. I is equal to the square root of -1. So that tells us that I squared is -1. I cubed is -I, and I to the 4th is a +1. So it's a circle, it's going around. So I to the 5th is going to be the square root of -1, I to the 6th is -1, I to the 7th is -I to the 8th is 1, and it's going to go around and around and around as it goes. So I have one problem left on our practice test that I've sent you guys, and it actually wants us to simplify or multiply, what you see down here, two complex numbers together. And it is problem number 29. 29. It's on here somewhere. There it is. There it is. So we're going to run through this problem one time, and hopefully it'll make sense, and I'll let you be free for the afternoon. So camera 2. Here we are. Number 29 says, what is the product of the complex number -3i plus 4 times 3i plus 4? So product, that's a vocab word. Product means to multiply. Anytime you see that word, it wants to know what the two numbers are multiplied together. So it says, what's the product of We'll use black. Negative 3i plus 4 times 3i plus 4. So these look familiar, or should at least, because I did some problems earlier where it looked, right, stuff inside parentheses and there was two of them and I was multiplying together. And I think what I did was I FOILed, right? So that's the trick here as well. It always is. Whenever you see a thing in parentheses times another thing in parentheses, the trick here is to FOIL. So we're going to do that. I got negative 3 times a positive 3, and then 2i. So negative 3 times positive 3 is negative 9, and I times I is I squared. So that's first. On the outside, I have negative 3 times a positive 4 is a negative 12, and I have one I going along for the ride there. Here I have, on the inside, I have 4 times positive 3, so this is going to be a positive 12, and I have one I going along for the ride there. And I have 4 times 4 for my last term, which is 16. Notice that this is turning out nicely because my single I terms, where I is equal to the square root of negative 1, are canceling out. I have negative 12i here and a positive 12i here, so I can just swoop those out, and they're gone. And now I am left with 16 basically minus 9i squared. And if you remember, I had I squared is equal to negative 1. So remember that I equals square root of negative 1, so I squared is equal to negative 1. So I'll substitute that in. I have 16 minus 9 times negative 1. 9 times negative 1 is negative 9, so this is 16 minus negative 9. And when I have two operations that are when I'm operating on an operation that doesn't make sense, I need to know how to deal with this situation. So that's equal to 16 plus 9. 16 plus 9 equals 25. So negative 3i plus 4 times 3i plus 4 is a positive 25. Just double check my answer on that, although I feel rather confident. Yes, it is 25. And you can see here, that's a choice right there. Zoom in a little bit. C is 25. All right, and so that's pretty much it for complex numbers. The trick there is really just knowing what I represents, what it means. It's the square root of negative 1. So anytime you feel like you're taking the square root of a negative, just to be clear, your calculator will not do that for you. If I take the square root of negative 1, non-real answer. So your calculator won't do complex numbers for you. But the best thing that you can do is recognize that when you square I, you get negative 1. So that's the big trick there. All right. Thank you all for listening. Once again, I hope this is useful. If you guys have questions, it's inspiredclassroomtim@gmail.com, and I am more than happy and willing to help you with anything that I can. So hopefully we'll hear from you soon, and hopefully this has been good. Cheers. Have a good afternoon.